Welcome back to our ongoing exploration of number theory.
Yeah.
Today, we're diving into the fascinating world of divisibility rules.
Okay.
These aren't just neat tricks.
Right.
As those of you in STEM fields know, they're rooted in solid mathematical principles and can be real time savers in calculations.
Exactly. Divisibility rules give us a shortcut,
Mm-hmm.
a way to tell if one number divides evenly into another without actually having to do the full division.
So let's jump right in.
Okay.
We've got divisibility rules for a whole bunch of numbers. But today we'll focus on the rules from 1 through 30
Okay.
and then explore what lies beyond.
Sounds good.
Even within that range, you find a surprising variety of rules.
You do?
Take the rule for divisibility by 7.
Okay.
For example, there's the method where you subtract twice the last digit from the rest of the number.
Right.
And if that result is divisible by 7, so is the original number.
Exactly.
I've also seen a method that uses a repeating sequence. 1, 3, 2, 1 if 1, and even 2.
Mhm.
What's interesting is that both methods work because of the underlying math,
Yeah.
principles of modular arithmetic and properties of multiples of 7.
What's fascinating is that these seemingly simple tricks have solid mathematical backing.
Yeah.
And it's not just 7 that has multiple methods. Divisibility by 13 also boasts a few different approaches.
I know 1 for 13 uses a similar repeating sequence. 1, next 3, -4, -1, 3, 4.
Oh, wow.
It really highlights the rich tapestry of patterns we find in number theory.
And of course, we can't forget the classic rule for 11,
Right.
where you form the alternating sum of the digits. If that sum is divisible by 11, the original number is as well.
Right. So to check if 253 is divisible by 11,
Okay.
you'd calculate 2, 5 plus 3, which equals 0.
Right.
And since 0 is divisible by 11, we know 253 is 2.
Exactly.
But what happens when we start looking at numbers beyond 30? Does every number have its own unique rule?
Well, for composite divisors,
Okay.
numbers made up of multiple prime factors,
Uh-huh.
you can leverage the rules for their prime factors.
So if we want to check for divisibility by, say, 36,
Okay.
which is 4 times 9.
You'd simply check if the number is divisible by both 4 and 9.
Okay.
If it is, then it must also be divisible by 36.
Got it.
It's like a divisibility chain reaction.
That makes sense.
Yeah.
But what about prime numbers larger than 30? Do they have special rules too?
They do, and this is where things get really interesting. We can actually derive divisibility rules for prime numbers using something called an inverse modulo, the prime.
Okay. I know we have a lot of STEM folks listening in, so modular arithmetic might be familiar territory.
Mhm.
But for those who haven't encountered it before, could you break down what an inverse modulo of prime actually means?
Of course, in modular arithmetic, we're focused on remainders. So let's take an example.
Okay.
Say our prime number is 7.
Mm-hmm.
To find the inverse of 10 modulo 7, we need to find another number that, when multiplied by 10, gives us a result that leaves a remainder of 1 when divided by 7.
Let me see if I'm following. So if we multiply 10 by 5, we get 50.
Right.
And 50 divided by 7 gives us a remainder of 1. Does that mean 5 is the inverse of 10 modulo 7?
Exactly. You got it. And once we have that inverse, we can use it to create a divisibility rule.
Yeah.
There's a generalized method that uses this idea of inverses.
Okay.
It works especially well for prime numbers.
So instead of going through a bunch of individual rules for primes, we can learn this one powerful method.
That's right. And it also helps us understand the deeper structure behind these rules.
That's what I love about number theory, uncovering those hidden connections now. Before we dive into the details of this generalized method, I'm curious, are there any resources you'd recommend for listeners who might want to explore the proofs behind these divisibility rules in more depth?
Absolutely. For a classic text, you can't go wrong with Introduction to Analytic Number Theory by Tom M. Apostol.
Okay.
And for those who prefer a more visual approach, there are some fantastic videos and interactive websites that break down these concepts step by step.
Perfect. I'll be sure to include some links in the show notes for our listeners now. Yeah. Let's talk about the practical side of things. For people working in STEM fields, these rules can be incredibly useful tools, wouldn't you say?
Definitely imagine you're a computer scientist working with massive data sets.
Mm-hmm.
Instead of performing computationally expensive division operations, every time you can use divisibility rules to quickly filter out irrelevant numbers, this can dramatically speed up your program's performance.
It's like having a secret weapon in your coding arsenal. And for those in fields like engineering or physics, where precision and efficiency are paramount, knowing these rules can be invaluable.
Absolutely. Let's not forget the role divisibility rules play in cryptography, too.
Ah, yes, the art of secret codes. How do divisibility rules come into play there?
Many encryption algorithms rely heavily on prime numbers, and their properties divisibility rules can be used to test the primality of large numbers, which is essential for generating those secure encryption keys. So in a way, divisibility rules help safeguard our digital communications.
That's incredible. These seemingly simple mathematical tricks have such a significant impact on protecting our online privacy and security. It really highlights how interconnected different branches of mathematics are and their real-world applications.
Precisely. And, even outside of specific fields, just in everyday life, divisibility rules can come in handy, splitting bills, evenly figuring out if you have enough ingredients for a recipe. These rules are all about recognizing patterns and simplifying your thinking.
I use them all the time. Without even realizing it, it makes you wonder, were these rules always known? Or is it something that developed over time?
That's a fascinating question. The concept of divisibility itself is a fundamental mathematical principle, one that's been explored across cultures and throughout history. And as mathematicians delved deeper into the world of numbers, they uncovered these patterns and relationships that we now know as divisibility rules.
It speaks to that universal language of mathematics no matter where you're from or what language you speak. The logic of these rules shines through.
It's a reminder that even though we come from different backgrounds, we have this common ground in the pursuit of mathematical knowledge, and it's a pursuit that's accessible to everyone. I know a lot of our listeners might be teachers or educators, and I think it's worth pointing out that divisibility rules are a fantastic way to introduce young students to number theory concepts.
I completely agree. Instead of just memorizing multiplication tables, kids can start to see those underlying relationships and patterns in multiplication and division. It's like unlocking a secret code.
Exactly. And who knows, maybe one of those students will be inspired to make the next big breakthrough in number theory.
Well, on that note, we've come to the end of part 2 of our deep dive into divisibility rules.
Oh.
Be sure to join us for our final segment where we'll tackle that generalized method and maybe even try our hand at creating our own divisibility rules. Welcome back to the final part of our divisibility deep dive.
Yeah.
I'm really excited to explore that generalized method for finding divisibility rules,
Totally.
especially for prime numbers.
Yeah.
It's a powerful technique.
It is.
And it all hinges on that concept of inverses modulo, a prime that we talked about earlier.
Right.
Right, finding that special number that when multiplied by 10 gives us a remainder of 1 when divided by our prime.
Exactly.
So how do we use that inverse to create a divisibility rule? Walk me through it.
Okay, so let's take an example.
Okay.
Say we want to come up with a rule for 37.
Okay.
First, we need to find the inverse of 10 modulo 37.
And we could use the extended Euclidean algorithm for that, right?
Yep.
But I think you mentioned there might be a simpler way for this particular case.
There is a bit of trial and error, can sometimes be faster for smaller primes.
Okay.
Notice that if we multiply 10 by nadical 6.7,
Mhm.
we get nadical 67, and nadical 67 divided by 37 leaves a remainder of 1.
Ah, so our inverse can be a decimal. I hadn't thought of that.
Exactly. In modular arithmetic, fractions are perfectly valid. So our inverse for 10 modulo 37 is nadical 6.7.
Okay.
Now let's say we want to test if the number 814 is divisible by 37.
Okay, so we take our number 814, and what's the next step?
We take the last digit 4 and multiply it by our inverse negative 6.7 that gives us 9 is 26.8.
Okay.
Then we add that result to the remaining digits, 81.
So 81 plus negative 26.8 gives us 54.2.
Right.
And if 54.2 were divisible by 37, then we know 814 is also divisible by 37.
Precisely. In this case, 54.2 isn't divisible by 37, so we know 814 isn't either.
Wow, that's really neat. It feels almost like magic, but it's all based on solid mathematical principles.
That's the beauty of number theory, finding these elegant connections and patterns within the world of numbers, and with this generalized method, you can unlock a divisibility rule for any prime number.
So if we wanted to find a rule for, say, 73, we just need to find the inverse of 10 modulo 73 and follow the same process.
Exactly, and that's where that extended Euclidean algorithm can come in handy for finding those inverses, especially for larger primes. It might seem a bit daunting at first, but it's a powerful tool, and with a little practice, it becomes quite intuitive.
It's amazing how everything ties together in number theory. Modular arithmetic inverses, prime numbers, these clever algorithms. It really makes you appreciate the depth and interconnectedness of mathematical ideas.
It does, and it's just the beginning. There's so much more to explore in the realm of divisibility and beyond.
Well said. It feels like we've only scratched the surface today, and on that note, we've come to the end of our deep dive into divisibility rules. I hope our listeners have enjoyed this journey into the fascinating world of number theory as much as we have.
Absolutely. It's been a pleasure.
Thanks for joining us, and until next time, keep those mathematical minds curious and keep exploring the wonders of numbers.